People, chapter 1 starts off with chemicals, what they are and where they come from. Now, people, right at the bottom of the page, you don't have to worry about that first part. Chemistry is simply the study of matter, okay, what the substance is made of, and why it behaves in the way it specifically does during a chemical reaction. All right. Now, in chemistry, we try and find patterns so that we can use these patterns to predict how things will react. For example, you all know that when an acid and a base react, the product is a salt and water. That could be considered to be a pattern, which we can use to predict what different acids would react to form. Yeah. All right. So, they say we can ask useful questions like how can we obtain useful materials from the earth and how can we make new substances. Now, people, for example, the plastics industry is a rapidly growing industry. They design new materials every single day. Some are useful, some are not. All right. Although plastic was thought to be extremely useful, and it is, but nowadays there is a very, very large problem with plastic pollutants. No, plastics are persistent. They don't want to degrade. Yes? Yes, but then it releases carbon. Plants can't use carbon. They use carbon dioxide. It's one of the ways of disposing of it and trying to get it back into the cycle, but it's not a perfect method. Okay. If it decomposes under bacterial decomposition, then it usually ends up as carbon dioxide or methane, which can be burned to form carbon dioxide and water vapor, which can be used by the plants again. All right. So there are problems with that, but that's environmental chemistry. All right. Now, the next section there in your textbooks, page 3, solids, liquids, and gases. In other words, the kinetic theory. What does the kinetic theory tell me? Yes, particles. Matter consists of particles. These particles have energy so they can move. There are spaces. And there are forces between particles. Two types of forces, attractive and repulsive forces. Okay, now solids. Solids consist of particles. What do we know about the movement of the particles in solids? Yes, they vibrate around a fixed position. In other words, in solids we say particles are orderly arranged in a crystal lattice. The movement is a vibration about a fixed position. What do we know about spaces in solids? They are very small, all right. The attractive forces are quite strong because it holds it rigidly in position. The repulsive forces we know, whether it's a solid, liquid, or a gas, when we start forcing particles together, then the repulsive forces come into action. But if we don't force them together, we can just ignore the repulsive forces because there are no repulsive forces in this pen. All right, until I start smashing the particles together, then the repulsive forces come into action. All right, so that would be the kinetic theory with respect to solids. In terms of liquids, matter consists of particles. How can I prove that in terms of liquid? If I poured some water out on the floor, tomorrow morning I'll come back. Will there be any water left? No, it will have evaporated. Okay, so the tiny particles have escaped from the liquid and it formed a gas, so it's disappeared. All right. Also, I can make, on a cold morning, I can make water vapor condense into droplets. Okay. So, in a gas, we have particles. The particles can move. What do we know about the movement in gases? We call the movement diffusion. So the movement of liquid and gas particles, we refer to it as diffusion. Technically, solid particles can also diffuse, but it is so slow and so little over such a long period of time that we ignore it. Okay, we just completely ignore it. So diffusion, if I'm referring to particles moved by diffusion, I'm talking about a liquid or a gas. Okay. So they move, they can move freely. Definition of diffusion is spontaneous movement of particles. Okay. So, what do we know about the spaces in a liquid? Can I compress a liquid? No. Can't compress a liquid. Can I pour water in a bottle and compress it? No. Yes. Okay, so the spaces are fairly small. We say bigger than in a solid, but smaller than in a gas. Attractive forces in liquids are slightly weaker than in solids, because in the liquid state, it has partially overcome the attractive forces holding them in a fixed position. Yeah. I don't know. Pity. Okay. Yes, but under normal conditions, it's very, very, very slightly compressible, so little that we ignore it. But I don't know about hydroforming. Okay. People, then, once again, the repulsive forces play a role when we start forcing them together. Okay. When we look at a gas, gases consist of particles. I know that because if I have a smelly gas on this side of the room, within a few moments on the other side of the room, you can also smell it. How did it happen? Well, the particles would have had to move. So the particles went into your nose, dissolved there in the moisture on the nerve endings, okay, and we can smell the smell. So gases consist of particles. These particles move by means of diffusion, and I'll have a look at diffusion just after this. There are spaces between gas particles. What do we know about the spaces between gas particles? Small or big? Very large, because gases just tend to spread. So if I have a bicycle pump and I pulled some air into the pump and I closed the front, I could squash the gas. All right. So we say gases have fairly large spaces. The attractive forces in gases have been overcome completely. So the attractive forces are so weak, we say there aren't any. Nothing holds the gas particles together. Because if I open up a cylinder of gas, it spreads. And if I open up the classroom, it will spread further. Okay. So the attractive forces in gases are very weak, so weak that we say they are non-existent. And then repulsive forces, once again, when I start forcing particles together. Okay. In your textbooks, there they have a look page 4 and page 5 at the kinetic theory for solids, liquids, and gases. Then they have a heading there, Brownian movement. Okay, what is Brownian movement? All right, Brownian movement, die rympie, zigzag, erratic movement of solid particles suspended in a liquid or gas. So we have two phases. We have a solid in a liquid, or we have a solid in a gas. The easiest illustration of Brownian movement, if you sit inside a room with the curtains drawn, a shaft of light shines between where the two curtains come together. You can see the little dust particles just moving aimlessly, dancing about in the air. That is Brownian movement. The dust particle is the solid particle, and the air, we can't see that. The solid particles bump into the air particles, and they move erratically. All right. The difference between Brownian movement and diffusion, in Brownian movement we have a solid particle suspended in either a liquid or a gas. But in diffusion, it is the particles of the liquid or gas that moves. In other words, if there wasn't diffusion of gases, would we be able to observe Brownian movement? No, because the air particles diffuse, they are moving. And they bump into the solid particles that are very light. okay, we get the Brownian movement. Do you understand that? Okay, even though this classroom is closed up, because we have air in it, there is diffusion. Some of the textbooks keep on saying that diffusion occurs from a point of high concentration to a point of low. Yes, it does. But if the concentration is spread uniformly throughout, it still keeps going. It doesn't stop. Do you understand? All right, that is quite important because that's a misconception that they sort of tend to confuse everybody with. All right, so in your textbooks there on page 5, we have Brownian movement. Now, still there on page 5, in terms of diffusion, one very well-known experiment, we take a horizontal tube. On the one end of the tube, we put in HCl, and on the other end, maybe I should have done it the other way around. Maybe I should have done some acid, HCl, and over here we have NH3. Okay. They put 2 cotton wools soaked with each of the solutions simultaneously into this tube. Now what happens is when hydrochloric acid and ammonia meet, it forms ammonium chloride. And this stuff is white, smoky. It looks like smoke. All right. It's actually tiny solid particles that are formed. Okay, ammonium chloride. Now, if diffusion of the different gases occurred at the same rate, we would expect them to meet somewhere in the middle. But this doesn't happen. Where does it meet? It forms the ammonium chloride ring closer to the hydrochloric acid than to the ammonia. What is the explanation of it? Smaller, lighter particles can move faster than bigger, heavier particles. Do you understand that? All right. So, in terms of diffusion, not all gases diffuse at the same rate. We tend to find that the lighter gases diffuse faster than the heavier ones. That's the first factor. The second factor, if I went and investigated diffusion in gases in relation to diffusion in liquids, we are going to find that diffusion in gases occur quite rapidly, while diffusion in liquids takes slightly longer. All right. If I take a smelly perfume and I release it on one corner of my class, within moments you can smell it in the next corner. But if I took a container and I dropped a single drop of blue ink into it, it takes a couple of seconds for this ink to slowly disappear as it spreads into the water. Do you understand? So, the second factor then that influences the rate of diffusion is the phase. Gases diffuse faster than liquids. Why? In gases, what do we know about the attractive forces? Almost non-existent. They've been overcome. In liquids, the particles are still under the influence of the attractive forces, so they aren't completely free to just move. All right? They are held together very slightly by these forces. The third factor then that will influence diffusion is the temperature. And just very simply, temperature is a measure of the average kinetic energy of the particles. So at a higher temperature, particles have more kinetic energy. If they have more kinetic energy, they can move more. All right. So hotter temperatures, faster diffusion rates than lower temperatures. If I did the exact same experiment in a fridge or in the freezer, then it will take much longer to form this ring, although it will still form closest to the hydrochloric acid. Okay. Is julle met my? On a hot day, it's going to go faster than on a cold day. Yes, yes. If you warm the one, it's going to go faster than the other. Okay, so I can mess around with this experiment. I can go and warm up this. Okay. Yes, then it's going to go, it's definitely going to go faster, no? All right. So 3 factors that influence the rate of diffusion. Okay, Joshua. All right. That is there in your books on page 5. Now, the next section, this chapter is so 'n bietjie los en vas. Okay. This next section, the heading is making useful substances, and it sort of goes about how do we separate things from each other. If I have a bag of sugar and some other kid has been messing around with it and mixed it up with some sand, how can I separate the sand and the sugar? I would dissolve, put everything in water. The sand's not going to dissolve. The sugar will dissolve. I can filter it. I'll be left with the sand, and then I can evaporate off the water. Okay, so a lot of these things are just common sense. If I have iron filings distributed among salt grains, how will I get the iron filings out? I will use a magnet, because one of the components is magnet. Yes, because you don't get the filings off the magnet. Okay, so this is what this next section is about. Yeah. Okay, sugar and salt. For example, I could use petrol. Both sugar is molecular, okay, because it's covalent bonds between the carbons and the hydrogens and the oxygens. And salt is ionic because it's a metal bonded onto a non-metal. We'll come to the bonding in the next section. Now, in general, there is a rule that says like dissolves like. Water is the exception because it's a polar molecule, so it tends to dissolve both. But petrol, for example, is a molecular liquid. So sugar will dissolve in petrol, but salt won't. So I could shake it up in some petrol. I can filter off the salt, and then we can wash the sugar from the petrol with water. The petrol and the water won't mix, so I add, shake it up. The sugar will dissolve in the water because it's more soluble in the water than in the petrol. And by doing that, you can rinse, well, you can wash the petrol and to remove the sugar. So it's not impossible, but you need to know certain things to do that. But that is what they do when they go and start working with these funny things. All right, so in your books there on page 6, separating mixtures, they say mixtures of solids and liquids like seawater, we can evaporate off the water, we'll be left with the salts. Mixtures of 2 or more solids, such as the ore in the extraction of metals. Now, we haven't done that chapter yet. You only do that in grade 12. But the first one of the first crude steps is to remove all the impurities from the ore. We don't want all the rocks and sand. We specifically want the ore. So there are specific ways. They use specific solvents that they know will dissolve certain things. All right, like the sugar and the petrol. Then mixtures of 2 or more liquids. How would I separate them from each other? Yeah, petrol and alcohol. They have different boiling points, so I can do a distillation of the liquids. If they don't mix, water and oil, I can decant. I can just run the one off from the other. You get a special decanter that opens on the bottom, so you run the more dense liquid out first. And you can close the tap and you're left with a less dense liquid in the container, or you can just pour it off. Okay. So that is just basically what they refer to. 2 or more gases. Well, gases can also be done by distillation. They're going to have a look at mixtures of solids and liquids. Now, when I have a mixture of a solid and a liquid, for example, I take sugar and I've got it in water. If I've got sand and water, I can filter it off because the sand is not soluble. Now, well, let's say I have pure sand with no other minerals and stuff in it. Okay? The sand won't dissolve, or the one component doesn't dissolve, then I can filter it. Okay? Yes, you can also leave it to settle. The heavier particles go down, and you can decant some of it. That would also work. If I have a substance that dissolves in the liquid, like sugar that dissolves in the water. Well, if I wanted the water afterwards as well, then I would have to do a distillation because the water will boil off and I'll be left with the sugar. But if I don't need the water, I can just evaporate off the water and sugar crystals will be formed. Okay. Sometimes I have, if I want to make copper sulphate crystals, I've dissolved the copper sulphate in my solution. I will evaporate off some of the water until my solution becomes saturated. And then I will leave it to stand and it will form crystals in that solution. And then I can just pour off the liquid and I will be left with pure crystals. They talk about the process of crystallization. Okay. We use crystallization to make salt in Walvis Bay. We have these dams of seawater that have been pumped into big pools, all right, and sunlight evaporates the water. And as the water evaporates, the least soluble salt in the water crystallizes first. So then they can pump it to a next dam, and that one evaporates more water, and then the next soluble one will crystallize, and in that way we can remove the salt.
It's ShopRite's big low-price birthday. We're celebrating with big deals and even bigger savings. Like 10 kilos Pocomo Fat Cook wheat flour for only $109.99 and 750 grams Ricoffee instant coffee for just $79.99. Don't miss out on our big low-price birthday. Only at ShopRite.
Brownian Movement, and then Brownian Movement in comparison to diffusion. How do they differ? What is diffusion? Yes, Brownian Movement is a solid particle, very tiny solid particles that don't just fall down to the ground because they are so tiny and so light they get bumped around by the air particles or the liquid particles. Yes, then you can see the little dust particles floating around. That is Brownian movement. So it's a solid particle that is suspended in either a liquid or a gas. While diffusion is just very simply the spontaneous movement of particles. If there was no diffusion, we would not see any Brownian movement. Because as a result of the random movement, for example, of the gas particles, they bump into the dust particles. We can't see the gas particles, but we can see the dust particles when light reflects off them. Okay. So they are connected, but it's not the same thing. We get Brownian movement because of diffusion. Okay. You can compare Brownian movement to, for example, if I put a balloon into the air and I say to you, keep it up in the air for this period. You will smack it upwards and it will come down, and you will smack it upwards and it's going to float. Okay, that would represent Brownian movement. You would be the gas particles, the balloon would be the solid particle. Okay. The next section then, there on page 6, refers to making useful substances. And over here it's about how to separate different things from each other. I think we just started with this. Sometimes it's easy to separate things. If I've got large enough pieces, if I must separate sand from bricks, what will I do? I'll throw it through a filter with small enough spaces for the sand to fall through and the bricks to be left behind. Or even more, on a more basic level, I can physically pick up the bricks and pack them one side, and I will be left with sand and bricks. But sometimes it's not as simple as that. If I go and have a mixture of sand, of sugar, sugar and sand. Now I can go and sit physically and pick them out. It's just going to take very, very long, but it's not impossible. But there's an easier way. I can put the sand and sugar mixture into water, because the sugar will dissolve in the water, but the sand won't. Then I can filter it off, and I'll have sugar water. I can evaporate off the water, and I'll have my sugar again. Well, pepper will float on water. It's not soluble. Salt is. So it's easy if the one part is soluble and the other part is insoluble. Because then you can dissolve it in a solvent, and the insoluble part you filter it out. And then you evaporate off the solvent. But what happens if I have sugar and salt? No. Okay. Yes. Yes. Okay, people. There's a rule. It's a very basic general rule in chemistry. And the rule simply says, like dissolves like. In other words, if I have a molecular liquid, it tends to be able to dissolve molecular solids. If I have an ionic liquid, it tends to be able to dissolve ionic substances. But we've got water in between. Now, water is molecular, but water is a very special molecular substance. Why? The molecule is polar. It's got a slight positive and a slight negative side, which means that water can sometimes dissolve ionic substances. So if I have sugar and salt, I can shake it up in water, but I'm going to get sugary, salty water. I won't be able to separate it. He says we use petrol. Why? Because petrol is molecular. It's got a low melting and boiling point. No? It evaporates fairly easy. It's molecular. So you can shake up the sugar and the salt in some petrol. Which part is going to dissolve, sugar or salt? The sugar will dissolve. Okay? Then I can filter off the salt. Now I must get the sugar out of the petrol. Now one way is to evaporate off the petrol, but in actual fact what happens is it'll contaminate the sugar. But what you can go and do is, water does not dissolve in petrol. So what they're going to do is they wash the petrol. They add water to the petrol with the sugar in it, and they shake it up. The sugar is more soluble in the water, so it's going to dissolve in the water, and they can, yes, into the water, and then they can decant the petrol from the water. You must be careful to wash out all the sugar, because the moment the sugar gets into the system, because of the heating and the burning of the fuel, the sugar, when it burns, it forms sticky, tarry, black carbon. If you've washed it properly, yes, you can. But you would maybe have to wash it a second and a third time. You understand? Yeah. So that it is usable, but it's not impossible. Okay, it's not desirable. Because the organic substances, the petrols, you mustn't swallow them. Okay? They can give you a chemical pneumonia. That's one of that. That's why when kids swallow furniture oil, it's so dangerous. They can get a chemical pneumonia, and the chemical pneumonia. That's even worse because there's acid in it. Yes, and there's acid in the batteries that can affect the different parts of your colon. Yeah. Mm? No, that's crazy. No, not good. I don't know, but it's not good at all. That's rubbish. Yeah, he's not drinking it. Yeah, for sure, that's rubbish. Okay, so in your books there on page 6, they refer to how to separate different mixtures. The first paragraph they have there right at the bottom of the page, mixtures of solids and liquids. It's easy if the solid is insoluble in the liquid, then we filter it off. If they are both, if the solid is soluble in the liquid, well, then we must get a way of removing it from that liquid, either washing with water or evaporating off the liquid, leaving you the solid behind. If it was sugar and water, I can evaporate off the water, and I'll be left with my sugar. Okay, so that is there on page 7. If I have sugar and iron filings, how would I separate them? A magnet, because the iron filings is magnetic. So it's still a way of mechanically sorting it. I'm just using a magnet. Yes, you can. They do in the mining industry. They allow the ore to fall down a chute, and as a result of the friction between the chute and the ore, they tend to pick up a static charge, the ore one charge, and the waste another charge. And it's a very crude separation, but it does work. Okay. So the next heading there, mixture of 2 or more liquids. If I have water and alcohol, how am I going to separate them? I'm going to boil it, because when I have mixtures of liquids, we must look at, are they soluble in each other or are they insoluble? If I have oil and water, I can just decant it. I can get a separating funnel, and I will add the liquid into it. Where did this come from? Separating funnel is a long funnel like that, and it's usually got a little tap there. So if I have got water, there's my water, and I've got oil, there's my oil. What is going to happen if I open up the tap? Well, the water will run out until the level drops, goes down, 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 last of it, and so the level of the oil will come down. Then we will stop. You follow? So we can decant it. You can roughly do it by pouring it off, or you can use what is known as a separating funnel. The problem comes in when I have something like alcohol and water. Alcohol dissolves in water. Now I can't decant it, so what must I do? And then? Yes, you must distill it. Okay? Can you remember, I think from grade 8 somewhere, you had an apparatus that looked something like this. Yes, the so-called Libby Condenser, and then around it is a glass tube with 2 openings. There's the one opening. Okay, so over here we will have our flask with the stuff that we are boiling off. So how does the Libby condenser work? The vapor is going to go into that inner tube. We will circulate cold water around the system, and the vapor is going to be cooled down with the cold water, and it will form drops that you can catch up in a container. We call this distillation. It's very important that the cold water goes in on the bottom opening and the hot water comes out on the top opening, because it's got to do with the efficiency of the heat exchange process. If I put cold water in here and my hot vapor is coming in here, they would stay in contact as such with each other, and the efficiency of the exchange process won't be very good. But if I have fresh cold water circulating up from the bottom, and I've got the hot stuff from the top, so it's in contact with new cold water all the time, and the heat exchange process is more efficient. All right, that is why we connect the tap onto the lower opening for the casing around the inner tube. Yes. Yes, it will be conduction. Okay, through the glass to the water. Okay, yeah? Yes, you will have to have a much colder setup here. You would have to pack it in dry ice or even lower temperature to make it condense. Okay, you would have to have a very efficient cooling system. Yeah? Oh, then they use, the coolant is, yes, you can use that. Yes, it's just, it's not sensible to use liquid nitrogen because it's expensive. Water is cheaper. But there will be some specialized processes where the thing is very volatile that will require a very low temperature to condense. Yes. Yes, or they will catch it up in a pressurized container and tap it off as it drips out. Do you understand? Some other system like that. But technically you can have any liquid. circulating through it. The reason why we, in general, for most of the processes use water is it's cheap and it's freely available. Okay? And it's not poisonous, where liquid nitrogen becomes complicated when you start working with it, because at the very low temperatures, the apparatus becomes brittle and, it can complicate things. But it's not impossible to use liquid nitrogen. Okay. So mixtures of 2 or more liquids. If you go halfway down that paragraph, there's a word fractional distillation. Now, fractional distillation is done, for example, if I have a container with many different liquids in it. There's the one liquid, there's the other liquid, there's another liquid, and there's another liquid in it. I've got different liquids with different boiling points. All right? What we then go and do is you can go and choose to start off, let's say the first one boils off at, let's say it boils off at 40 degrees. You can go and heat the system. You'll have your thermometer in here, monitoring it at 40 degrees, and then you can tap it down via your Libby Condenser. Okay? And then once you've tapped off all that liquid, then the next liquid, let's say its boiling point is 60 degrees. Then you can go and tap off the next one, and the next one, and the next one. But it will be a very long process. They usually tap off the first crude one, and then from there, they will take those 2 liquids, and they will do them separately. Okay? This is not very efficient. What they can rather go and do is, instead of connecting the Libby condenser like that, they connect a very long column onto the system. I'll come back to the diagram. It's slightly different from that. Okay? And what they go and do is, they will go and heat up everything. High temperature. Everything becomes a gas. And what will happen is the gases will rise up. We call this the fractioning column. But as they rise up, they will start to cool. And if they become cool enough, what's going to happen to the gas? It's going to condense. But we find that it does it on its own accord. Those were the lowest boiling points. In other words, those that become gases the easiest. They rise up to the top, and they condense at the top. And then the one with the next higher boiling point will come down on the next level, because it condenses at a certain height in that column. And they tap it off from there. They've got, it's a system of pans in this chimney with gaps in between. So some of the liquid can drop back. And then it just falls back at heat, and it goes back up again. All right. So then we talk about a fractional distillation. And this they do with crude oil. All right. Now, when we do organic chemistry next year, I've just started with the grade 12s, and they've just done the fractional distillation of crude oil. Okay. Then I'll come back to the fractional distillation. Yes.
But maybe the ones at the top drops and then drops into the...
It doesn't matter. It just vaporizes and it'll go back up again. Yes, it's not a perfect separation. There will be some cross-contamination, but they will take each of the separate fractions and do a separate distillation to purify to the level that they want. Because sometimes it doesn't matter if there's a little bit of the one mixed with the other. For example, with petrol, they fraction off different groups. The first one is methane, ethane, propane that they fill gas cylinders with. The next fractions that come off is petrol, between 5 and 10 carbons in a chain. And then the next fraction is diesel, between 8 and 50. It's a range. You can go and purify it further. It just becomes more expensive. Okay. So that would be fractional distillation. Now, in your textbook is the next question that you asked over there. If you look at figure 1.12, sometimes I have 2 liquids with a fairly close boiling point. Then they go and connect something called a reflux condenser. We will have our container, And to this container, they connect up a long column, all right, that is filled with, well, you can call it marbles if you like, but little glass balls or beads, all right? And what happens is that, and then down here at the bottom, they will connect the Libby Condenser. Have they got it on the top part? Right at the top, yes, for the vapor. Sorry, I mixed up. Okay, down there. So right at the top somewhere, they will connect it onto a Libby Condenser there with the glass tube around it. Okay, there. So here the drops will come out into a container. Now, why do they have this reflux condenser? Let's say we have got, these are all the beads, I'm not going to draw them in. But what happens is, if both the liquids form a vapor that we have in here, all right, they both form a vapor. They are going to rise up, but as they bump into the glass beads, they're going to lose some energy. And what we are going to find, the one with the lowest boiling point is going to be able to remain a vapor. The one with the next highest boiling point will condense and drop back into the container until all of the liquid with a lower boiling point has been fractioned off. Do you follow? Okay. So they can then do it this way. This is done when we have very close boiling points. Lowest one goes up the highest. So the one with the lowest boiling point is going to boil off first, because the one with the higher boiling point is going to condense and fall back into the container. Not always. Different gases have different densities. I don't know. I think it is probably less dense, but it's not the density that influences this as such. Okay. It's got to do the boiling point. It's not the density. You can get something with a low density that has a fairly high boiling point. Okay. Yes. 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 It's the forces between the particles. If I look at alcohol and water, alcohol is molecular, weak forces between the particles. Yes, to a certain extent, but it's not the density that affects distillation. Not at all. Okay. The least dense one will go to the top. But it also happens to be the one with the lowest boiling point during that process. Okay, because what happens is the bigger the molecule, the boiling point will also increase. So bigger, heavier molecules have higher boiling points than smaller, lighter molecules. In general, there are always exceptions. Yes, but you mustn't look at it in terms of density because it's going to confuse you. Okay, it's boiling point. All right. Okay, yeah. Yes. They will have a thermometer in the system, and they can monitor the temperature. If over here, for example, they will be able to monitor the temperature. Alcohol boils at 80-something degrees. Water goes to 90 or 100, depending on air pressure. Okay. But they will monitor it. There will always be some cross-contamination. For example, when they distill alcohol to make brandies and whiskies, they sometimes refer to triple distilled. Why is it triple distilled? To remove the water. Because alcohol likes water. It's hygroscopic. So some water always goes. That's why you only get a 40% whiskey. To get 100% alcohol is very difficult because it likes absorbing water. But it's not impossible. Yeah, well. Okay, let's go on. All right. So there on page 9, there is using melting and boiling points data to tell us how pure a substance is. The next thing If you have, yeah. Yes. Yes. You can. But usually when you want to distill it, you want both. For some other reason. Do you understand? Yes. The alcohol will burn. Yes. Normally you're trying to get the alcohol. Okay. But it's not impossible. You can burn the alcohol off. Okay. Using melting and boiling points, people from grade 8, what do we know about pure substances? Yes, pure substances have fixed melting and boiling points. Also, while something is melting or boiling, what happens to the temperature? It remains constant. When there's a phase change, temperature is constant. Okay? And in other words, if I'm boiling off one fraction, the temperature is going to remain constant, let's say at 80 while the alcohol. And when all the alcohol is gone, the temperature will rise to 100 where the water starts boiling off. And it will stay there. And if I have a different liquid that has a higher boiling point, it will, after all the water has been boiled off, it will go on to the next level. Okay. The next section in your textbooks, they're on page 10. How do we figure out if something is pure or impure? Well, there are various ways of doing it. A pure substance, we've just said, will melt and boil at a fixed, constant temperature. What would an impure substance do? This is old work. Yes, it will melt and boil over a range of temperatures. In terms of the graph, if I have a graph that looks something like that, all right, then I will know, okay, this upper point, is that going to be melting or boiling? It's going to be boiling. And the lower point would be melting. The lower temperature is always the melting, and the higher one is always the boiling. Okay? The moment that you have got impurities, various things happen. In the first place, the melting point goes lower and the boiling point goes higher, and we don't have a fixed, constant melting or boiling point. It doesn't remain constant if you've got impurities in the liquid as such. Okay, so we will in the first place find that these two parts would go lower and higher, and in general we will get a curve that tries to do something like that or have a different shape. There is not a fixed melting and boiling point. All right. Don't wake him. Yes. Impurities, simply lower melting points and higher boiling points. There's always an exception to a rule, but in general, melting point goes lower. Have you tried freezing water with salt in it? Doesn't want to freeze. That is why they add salt in Europe. Where the road starts freezing up, they add salt to the road. Keeps the water slushy. Yes. Yes. Yeah. It's got to do, why does it? It's got to do with the surface tension that changes when you dissolve something in it. And it's surface tension that holds the bubble. So if you can weaken, if you add certain things to it, you change the surface tension. Okay, and then the bubble will burst. All right. Or in terms of...
So that is why you add bath salts, so that it's better for you. Well, why do you add bath salts?
It softens the water. We have hard water areas. So it helps to remove some of the insoluble salts so the water becomes softer. That's why it feels nice and soft on your skin. And soapy-like almost. Yeah. Okay. So if I want to determine whether something is pure or impure, I will go and have a look at melting and boiling points. If something is pure, it will have a fixed, constant melting and boiling point. And I can go and look up. If I think that I have water, I will know, okay, water melts at 0 and it boils at 100. If I test the liquid that I've got, an unknown one melting and boiling point, I've probably got water. Alcohol freezes at a much lower temperature and it boils at something like about 80 degrees. The different alcohols will be slightly different. But we can test melting and boiling point in the first place to see whether the thing we have is pure. Because it is pure, we will have a fixed melting and a fixed boiling point. And also then it will have a constant melting and boiling point. So you can check it on the table to confirm what you have. No, chemically it's not pure because a solution impure implies you have a mixture, except the one component dissolves. Pure water, yes. No, pure salt water, that is colloquial language. Okay. Yeah, it means you've only got salt and water, but in chemically it's not pure, it's impure. Okay. All right. Now, we are going to have a look at something called chromatography in the next section. Now, chromatography is a way of separating different substances because they have got different solubilities. And with chromatography, it's actually very nice and visual because we can separate the colors in ink. Because different colors of ink, it's different compounds, they will have different solubilities. Okay? And on the chromatogram, now this is a very simple one, it's just filter paper. And what you're going to do is, you're going to draw a line in pencil on that filter paper, just very close to the bottom. And on each one, you can put a singular little spot of the ink. And we've tested different colors. I can't remember what color they were. Over here. We had purple and pink and green and black. This one was black ink. And that one was green ink. Okay, what can you tell me about the black ink and the green ink from this chromatogram? Yes? Yes, and what do you know, can you notice about the two blues? Yes? But they're at the same level. Different substances have different solubilities. Similar substances have similar solubilities. And what happens on the chromatogram, the most soluble substance is drawn up higher. The least soluble ones get left behind. Okay, we will carry on the next period.
India's Ranthambore Reserve in Rajasthan is home to the rare Bengal Tigers. Every year, John Isaac, an Indian-born photographer, travels from New York City to document the lives of these majestic animals.
In the last 10 years, I think my interest has grown tenfold, and I'm very particular about the survival of the tigers.
His goal is to make sure that people everywhere know about the grave danger Bengal tigers face: extinction. John holds seminars and photographic exhibitions from his visits to Ranthambore to raise awareness of the plight of these tigers. He's currently working on a book to document their dilemma. due to an increasing human population encroaching on their territory. According to John and wildlife experts, each tiger needs as much as 9 square kilometers to survive, just under 4 square miles. The relationship between tigers and people has always been difficult, but now, with much less territory to roam, tigers often wander into human settlements.
The conflict between the villagers and the tigers has always been there, and then government tries to compensate. If a tiger kills a goat or a cow, they pay a certain amount to the villagers.
In the past, tigers used migration corridors or routes followed by wildlife for travel between summer and winter habitats. Now these pathways have been taken over by people who use them as living quarters and to reap firewood.
We are trying to work with the communities living around and trying to reduce their forest dependency so that we can conserve this corridor patch for the smooth and easy movement of tigers.
Jamuna Devi, a farmer, lives near one of the migratory corridors. She used to depend on the forest for grazing pastures. Now, thanks to a World Wildlife Fund initiative, Jamuna no longer needs to rely on the forest for her family's survival. The secret? Introducing new alternative crops closer to her home.
गई साल बोया हमने खुद ने, और ये तो अभी यही साल बोया है, ये आया होया कांदा है हम 25 रोज को तो तारीख को तो बोया ही है, और रोज बा में अंतर तो आगा भूलने लगा.
The success of this project has led to even more changes. Jamuna decided to plant fodder for her cattle on her excess land to further preserve the habitat of the tigers. She has also switched to cooking gas so that she doesn't have to collect forest wood for fuel.
जंगल में सब दुनिया ने जावे छोड़ दिया तो सब बे होगी, कोई काम नहीं करे, लकड़ी को भी नहीं करे, जंगल में जाने से भी परेशान है दुनिया. गैस भेज दिया सबन के घर घर में, वे सभी सिलेंडर पकड़ते हैं, और रुपया को कोई समझते ही नहीं है, अब भीतर भरा लावा.
Climate change also has a direct impact on the habitat of tigers.
The last 2 or 3 years, they say, there's been a drought. The rains have not been regular.
Climate change is a serious problem in this country, even it's in the continent. So keeping these forest areas alive and protected is the only solution. This year we have raised a nursery of 10,000 saplings. Forest department have shown their interest. They bought around 2,000-3,000 saplings.
The idea is to plant new trees to replace those lost to severe weather conditions and human activity. Poaching used to be a major threat to Bengal tigers. But thankfully, the number of big cats killed by poachers has plummeted due to measures implemented by law enforcement agencies, resulting in less demand for tiger products. Especially the introduction of camera traps and digital apps, which automatically take photos of moving tigers and suspicious persons moving around in the forest.
Every time I hear something like that, I feel so good, in some ways, some things are working, and so this is what drives me to come and do this. In my lifetime, if the tigers are extinct, I don't know how I'll handle that.